the derivative of the general exponential function y equals b dx. So let's just recall the exponential function. Okay, we know that it's always increasing when b is greater than 1, and it's always decreasing when b is between 0 and 1. So I never want to say when b is like a fraction or a decimal, because there are going to be improper fractions, so therefore the number is actually greater than 1, or decimals with like a whole number in front. But pretty much if b is between 0 and 1, so like that quote unquote fraction, is going to be decreasing the general exponential function. Okay, and we saw this in e to the x. They all go through the number 0, 1. Okay, just the base functions. Okay, the derivative of y equals b to the x is right here. Okay, the ln b times the function itself. But if we have a complete function in the exponent, what we're going to actually do is we're going to do the ln b times the function itself, then we're going to chain rule it. Okay, so quite easy. F prime at x equals 5 to the x. Okay, so in the exponent there's just an x, that's fine. We'll do ln 5 times 5 to the x. Okay, so ln of the base times the function itself. We can multiply it by 1 because the derivative of x is just 1, but it's tedious, so that's done. Okay, and for b f prime at x, we have to find the derivative of 5 to the 3x minus 2. So let's ln the base, so ln 5. Let's write the expression as it is, 5 to the 3x minus 2. Then we're going to multiply it by the chain rule. So what's in the exponent here? What is the derivative of 3x minus 2? And it's just 3. Okay, and just to simplify, bring it out front. So 3 ln 5 is our coefficient, and 5 to the 3x minus 2 is our function. Okay, example 2. On January 1st, 1850, the population of Gold Rush Town was 50,000. The size of the population since then can be modeled by this function. Okay, so we have f at x equals, of course, the starting 50,000, 0.98 to the t. Okay, 0.98, to me, that means that it's decreasing, and we're going to get an exponential function that looks like this, for an example. Okay, and this is because the 0.98 is between 0 and 1, right? It's that fraction less than 1. Where t is the number in years since January 1st, 1850. So first, they just want us to solve what was the population on January 1st, 1990. Okay, so 1990 minus 1850 is 50 years. So let's just go ahead and sub that straight in. So f at 50 equals 50,000 times 0.98 to the exponent 50. And when you take your calculators and sub that in, 50,000 times 0.98 to the 50, I get 18,208, and that's it. Because we're talking about people, so we're not going to put any decimals. We can't have a decimal of a person. Okay, so that was the population. Now B, at what rate was the population changing on that date? So what we just have to do is find f prime at x, okay? So when we see changing, we do the derivative. So we're going to pull out that 50,000. That's going to be the constant rule. And then we're just going to deal with 0.98 to the t. So we ln 0.98 times 0.98 to the t. And that's it, because the derivative of t is just 1, so we don't have to do the chain rule on that. Okay, was it increasing or decreasing at that time? Okay, so here's the thing. 50,000 is a constant, and so is ln 0.98. So if we put 50,000 times ln 0.98 in our calculators, we actually get the coefficient of negative 1010. I'm just going to round it there. And then times 0.98 to the exponent t. So this is the actual derivative, but now let's actually find the derivative when x is 50. So we can take the original or we can take the rounded. I'm going to go ahead and just take that original again. I just wanted to demonstrate what that rounded number meant. Okay, so ln 0.98 times 0.98 to the 50. Again, when we put that into our calculators, we get negative 367.86. Because the slope is negative, we can say that it was decreasing. Okay, so therefore, at this time, the population was decreasing, and it was decreasing by 360, maybe 8 people per year. Because remember, our t is measured in years.